All right, it is I. I am getting no, there we go. Son of a dog's breakfast. All right, we're good to go unless the storm here kills me. But you'll get to see it all on Zoom. Make sure it gets on the internet. Today, we will talk about GFS. I'm assuming you can all hear me?
We can hear you.
All right, good. So GFS is the Google file system, and it is the basis for HFS, which is Hadoop file system, Hadoop. MapReduce also came out of Google and a variety of other things. So this is actually fairly old now, 2003, so 17 years, wow, okay. So the Google file system was developed by Google, Natch, to provide distributed file system with high performance scalability, and fault tolerance. Okay, and so many distributed file systems have been developed prior to GFS, and all of them tried to provide these kinds of properties. And so Google took a crack at it, but they went about it a little bit different than an academic institution. Which is where most of the work had been done up to this point. Okay. And of course, as with all things Google, what they do is they've hired a bunch of the academics that are leaders in the field, and so they're bringing in people that have a lot of experience, both theoretical and some practical. And so now we're going to see what we can do in a practical environment with, in essence, an unlimited amount of resources. Okay. So GFS was designed around a number of observations. About Google's workload. And hardware environment. And so I think this is an important point to keep in mind, which is that Google wasn't building a distributed file system for the world. Google was building a distributed file system for Google. And so they predicated it, they founded it on what they do, the kind of data they work with, and the things that they need to support. And it turns out that that happens to be very generalizable to many, many different problems. And that's why GFS is popular. Okay. So the first was hardware. So they made this assumption that component failures are the norm. Okay, not the exception. So a lot of file systems are built around the idea that occasionally something will fail, and when it does, you need a way to deal with that, but that's a rare occurrence. GFS is built around the idea that failures happen all the time, and you need to deal with that, but it's a common occurrence. Okay. So the file system must assume and manage ongoing failure. So the basic idea would be that at any given time, Google says about 15% of the file system is broken. And that's the situation they're dealing with. And we'll talk about it later, but the reason why this is that Google also made the decision that they were only going to use commodity hardware for their file system backbone. And so there wasn't going to be any clever RAID arrays or high performance disks or lots and lots of overhead checking to make sure that things might go wrong, and so let's try to predict that and fix it. Nope, they just have racks and racks and racks and racks of blades with hard drives that you can buy at Best Buy or Newegg. And when a hard drive dies, which it does all the time, they get a message, and somebody walks out there, pulls the rack out of the blade out of the rack, opens it, yanks out the dead drive, throws it in the garbage, and replaces it with a new one. And so they have people at the file server sites just walking around doing this all the time. And so the reason they do this is because commodity hardware is cheap and it's readily available, and more importantly, improvements in hardware are happening at the most rapid rate normally at the commodity level. And so you're going to get all the improvements that you are seeing in the consumer space by just whenever you buy new drives, they're going to be better, bigger, faster, whatever it is. Okay. And so that was smart. They said, you know, let's not bother building anything fancy or buying anything fancy. Just use whatever a normal person would buy if they walked into a store. And that's what they do. And that's what a lot of file systems do. So that's what I do in our RAID array. I mean, I use RAID 5, and I don't buy, I think I buy Western Digital RAIDs, but I don't buy very fancy NAS drives because I've read that it doesn't really make a big difference. And besides, I have a system set up specifically so that when a drive dies, I just yank it out, put a new one in, and tomorrow the drive system will be back up and running properly. And it'll keep sort of chugging along even with that drive missing, slowly, but you know, chugging along. And so what do I care? I'm not going to spend an extra $200 on a drive. They almost never fail anyway. They're actually pretty reliable nowadays. Number 2 is access. So reading and appending are the norm. Overwriting and random writes are rare. Okay, so the file system is specifically designed to assume that you're going to read or you're going to add to the end of a file. You can overwrite or do random writes, but those are assumed to be rare, and so the system is not optimized for those. Okay. File size. So it is inefficient to manage billions of small files. Instead, these should be bundled into much larger multi-megabyte files. And I think this is something that you're expected to do at the application level. And so the way GFS works is that it's what's called a chunk size is big. And so what they tell you is, hey, if you're just storing a few bytes, you're going to be wasting a lot of space in that chunk. But you shouldn't be doing that. If you're just storing a few bytes, why don't you set up your system so that it bundles those little bytes together into a much bigger piece, and then store that in a chunk, and when you pull it out, unpack it, like pickle it or something. Easy, right? That makes it much less difficult and much less computationally expensive for the master to keep track of what's going on. And 4th is coordination. Coordinating between the file system and the application can simplify the file system without placing undue burdens on the application. Okay, so there's a very specific coordination scheme in GFS that's designed to be lightweight on the application, but also designed to be lightweight on the master coordinator for the GFS system, so that you're not killing the master, because the master is the bottleneck. The master is the first thing that you have to talk to kick off any interaction with the file system. And so the master tries to very quickly get you talking directly to some client that's holding the data that you want, and only talking to the master if something goes haywire, all right? So that it can handle all of the requests coming in from different applications for data, okay? So these are the four founding principles that GFS was built on. Any questions about those before I continue? Okay.
So, well, not so much a question, but the last part of like coordinating between the file system and the application, it'd be very difficult, I guess, for I guess a general purpose file system to be able to like come up with something like that. Like, oh, we're going to change how you interact with a file system, right? Like you'd have to almost be like a large organization like Google to say, hey, we're changing how your applications deal with files. I don't know. It seems kind of like because you're Google and you're coming up with this big thing, you're able to make some of those, I guess, assumptions or statements about how to use it versus a general file system. It seems like there'd be, even if it's saying undue burden, I feel like it'd be harder for just like any person to just be like, oh yeah, I'm going to do this other file system, and just I'd have to rewrite applications, etc. I don't know. Maybe I'm not articulating that well. I'm just wondering if that makes any sense.
So it's true that there is some change that you have to do to your application if you want to talk to a distributed cloud-based file system like this, or Hadoop or anything like that, AWS. But it turns out that the actual amount of change that you have to make is pretty minimal. So they've set up the API so that you have to do some initial setup, like who am I going to talk to, where are they located, and let's coordinate so that they know I'm allowed to talk to them. That's actually mostly done by the Google file system for you when you make the request. And then you just issue standard read-write requests with some additional information about this is the client that I need to get that information from. And so it's definitely not identical to just talking to something on the local disk, but it's actually not that different either. They've worked pretty hard to try to make it easy to migrate from disk-based to cloud-based. And in fact, if you write a program, you can use, so let's say you're writing in C, you can use some defines to make it really easy. So you can actually figure out right at the front end, which one am I talking to? And then you can just sort of pick one of two very similar read requests. So the nice thing is the program logic doesn't have to change at all. The only thing that's changing is when you go to get data, it could be a slightly different request, and maybe there's a little bit of setup at the front end required to make sure you can get that data. Yeah. So.
Okay, cool.
Yep. So pretty lightweight. They tried really hard to make it very minimal on the actual application, and so because they recognize that not everyone's going to want to go out and rewrite their entire application, nor can they afford to if they're going to use one of these file systems. Certainly within Google, since they're always using GFS, I don't think they ever bother with local disk unless they're just writing some hack code. And so,
sure.
Okay, so let me show you an example of the architecture. So this is built from many commodity components. Like I said, Best Buy hard drives. So this makes the file system cost efficient to implement. Extend or repair, right? So easy to set up, easy to extend. You just slap more commodity hard drives into another rack, another blade, and then repair is, like I said, you walk out, you pull out the dead hard drive, throw it in the garbage, and get a new one. So the GFS design is optimized for this environment. So a GFS cluster includes what's called a single master and multiple chunk servers. Okay, the master makes the file, the master maintains file system metadata. Okay, so no data, but it understands how the data is organized in the file system. And the chunk servers are responsible for managing chunk data on their local disks. So the chunk servers are where the actual data lies, okay? And each chunk is assigned a 64-bit chunk handle. By the master when it's created, okay? So the master knows all the chunks, and so it can assign a unique chunk handle to any new chunk that's created. All right. And for reliability, these chunks are replicated on multiple chunk servers. So you remember that GFS works on the assumption that failure is the norm. So that means that you would expect that at any given time, there's a high likelihood that one of the chunk servers is going to be down. And if it's the one that has the data you want, then you need to get it from somewhere else. So they keep multiple copies of it. So if chunk server A, which has your data, is dead, then you go to chunk server B. And if it's dead, you go to chunk server C. Okay. And again, the master will know where the replicated copies are located. So applications communicate with the master for file metadata. So that would be things like, for example, to get a file's chunk handles. All right. So a file is made up of one or more chunks, depending on how big it is. And so you can ask the master, hey, for this file, tell me all the chunk handles in order that correspond to the pieces of this file. And it will return those to you. And you can also you communicate with the chunk servers to read and write data. So since the chunk servers are the actual physical locations of the file itself, or the pieces of a file, that's where you're going to be talking if you're actually reading or changing the data. Okay. And so, as an example, to read a file, an application would complete the following steps. Okay, so let's look at the communication pipeline for an application that just wants to read a file. Who does it talk to, in what order, what data does it get, and how does that satisfy the requirement that it pull the file information? So first, you send the file name and the chunk index. Damn it. Oh well. To the master. So the file name obviously is the name of the file you want to read. The chunk index is the index of which chunk you want from the file, and you can figure that out because you know how big these chunks are. To obtain and cache a chunk handle and all chunk servers managing the chunk. Okay, so you're going to get back to chunk handle, and then you're going to get back all the chunk servers that actually contain that chunk with the given chunk handle, and that's the chunk that you want. So second, you'll send a read request with the chunk handle. Oops. And the byte offset, if there is one, to the nearest replica. So basically, it's like a typical read request. You say, you know, here's the chunk I want, here's the offset into the chunk. You probably also can tell it how much data you want, and then it'll return it to you. Okay? And then further read requests. Use the cache handle and replica list. Removing any further communication from the master. So removing any further communication with the master. And that's critical because you want to minimize the amount of strain that you're putting on the master. So the only time an app actually talks to the master is when it wants to figure out, hey, where is this data that I want to read? And once it knows that, it caches that, so it never has to ask again. And as long as everything goes the way it expects it to go, it just starts pushing out read requests and getting data from the chunk servers directly. And if there's no problem with that, if it's getting back what it wants, it just keeps doing that. It never talks to the master again. Okay? So chunks are sized, or were sized when this paper was written, to 64 megabytes. So this is much larger than a typical block size. So this is done for several reasons. All of which revolve around the assumption of large files and large sequential reads and appends. Right? So this is the assumption Google has because this is the kind of data Google normally deals with. And if you don't have this kind of data, you should rewrite your or update your application to deal with the data that it uses in this way. Otherwise, you're not going to get good performance from GFS. Okay. So what this does is it reduces the need for clients to interact with the master. Since local reads and writes occur on a common chunk. So the idea is that you want the chunks to be big so that a sequence of reads and appends are all going to happen on the same chunk because it's big. And that means you don't have to go back to the master and say, okay, I got to the end of this chunk, I need the next chunk, where is it? Because that's going to be different chunk handle, potentially different chunk servers. So you want to minimize the number of times you have to make that request, and so you just make the chunks big to avoid that. Okay. It reduces network overhead. By allowing persistent TCP connections between an application and a replica when performing operations on a common chunk. So since you're working with a chunk and it has a dedicated chunk server that you're talking to, you can actually build a TCP connection to that chunk server and just keep it open so that you can do synchronous communication back and forth to make requests, get data, give it data, append it to the chunk, and so on. And so that's great because actually building up and tearing down a TCP connection is relatively expensive. And so by having big chunks, you're not going to have to do that as often, and you're going to get improved performance. And then the final thing that they mention is that this reduces the amount of metadata on the master. So if you have big chunks, then the master has fewer chunks to deal with for a given set of files and file information. And so it's much more manageable than if you have tiny little chunks. And again, billions and billions of these things that the master is trying to deal with. And it's not just about storing the information, because the master is constantly dealing with making sure that that information is available and signaling when it's not, okay? And we're going to see that set of operations coming up. And so you don't want to have to be doing that for bajillions of chunks, okay? So any questions about why the architecture is the way it is before I move on to the metadata that the master actually stores?
I have a tangential question.
Sure.
Sorry, I know I ask a lot of these. So it's using TCP, but what is GFS like its own protocol? Like what other protocol are they using for actually sending and receiving data between the client, master, and chunk servers, etc.?
So I don't know what the actual protocol is that they're using, like under the hood, to send the data back and forth.
Mm-hmm.
But I'm pretty sure from the application's point of view, when it issues a read request, what it gets back is exactly what you would get back if you did an FREAD.
Okay.
Yeah. And so somehow the system is doing something to get the data back and forth, and then from your perspective, from the application's perspective, it just looks like an FREAD, except that you specified some sort of cached chunk handle, offset, and a chunk replica that you wanted to talk to. Yeah.
Got it. Cool.
Again, it's trying to be as faithful as possible to the basic local disk operations that you perform. Yeah. So. So what does the master hold on to up at its master level? Well, it's all metadata. There's no data. And there are 3 types of metadata. There's a file and chunk namespace. Makes sense. There's a mapping of files to chunk handles. And the locations of each chunk's replicas. Okay. So it has this file chunk namespace, so it knows that there's a set of file names in the file system with corresponding chunks, and it has some way of mapping the files to chunk handles, so the order of the chunks that make up the file. And then for each chunk handle, it knows where that chunk handle, where the chunk corresponding to that chunk handle, it knows where the chunks replicas are located. And so that's how, when an application says, hey, I want this file with this offset into the file, the system, the master can tell it, okay, go to these replicas, and here is the handle of the chunks that are going to hold what you're looking for. Okay, so namespace and this file chunk mapping are made persistent by storing them in an operation log. When the master starts, or restarts, it reads the log, then asks each chunk server to report which chunks it's storing. Okay. So the file namespace and the file chunk mappings are persistent on an operation log. So that means if the master starts or restarts for whatever reason, it can actually read the log, and then it can go to every chunk server and ask it, what chunks are you holding? And that's how it can figure out, okay, so where are the locations of the chunks replicas? All right. And the master periodically sends a heartbeat message to each chunk server. And these are interleaved, so it's sort of sending out heartbeat messages all the time, but they're going to different chunk servers. Okay, so this allows the master to verify the chunks on a chunk server. To garbage collect chunks that have been freed to update chunk replicas if the chunk server fails, and to migrate data between chunk servers to maintain load balance. Okay, so you have to remember that one of the consequences of the fact that you're not doing any work through a master when you're actually manipulating data on a chunk server is that there are things that are going to happen that the master's not going to know and is going to need to be updated about. So things like, oh, a chunk's been deleted. So that would happen down at the chunk server level, and during a heartbeat operation, the master would recognize, oh, that's been deleted. And so it would update its file chunk namespace and file chunk handle mapping, okay? And it also allows it to maintain some consistency. So it can figure out, like, you should have these chunks, and if you're telling me you don't, then something's wrong. So the simplest thing to do is just to basically yank you out of the replica list for all of these chunks and reset you with some new data because you seem to be in some odd state. Or if the chunk server doesn't reply within this timeout period of time, it'll just assume, oh, that chunk server's dead. And so it'll automatically create new replicas to hold the data that that chunk server used to hold. Not create new replicas, but migrate data to new replicas. And it can also move stuff around if it needs to, if it thinks load balancing needs to be maintained. So if it's seen a lot of requests for chunks on a certain set of chunk servers, it can actually try to move some of those chunks to other chunk servers so that sort of a small set of chunk servers is constantly being hammered for information by a whole bunch of applications. So that's sort of the basic guts of what the master has and a very high level explanation of what it's trying to do to keep consistency. Okay. Any questions about that before I talk about mutations, which are basically changes to a file as opposed to reads? All right. So mutations. So mutations, which would be writes or appends, change either the contents or the metadata of a chunk. Okay. So every replica of a chunk needs to be mutated consistently. So this is one of the standard issues with replication, is that when one replica changes, all the other replicas have to change in exactly the same way. And that operation has to complete appropriately or not be applied at all. You can't have some chunks that actually completed the operation and other chunks that didn't, because now you're screwed, because different chunks have different information, and when you go to read that information back, it's going to be ambiguous about what you get. Okay. Moreover, multiple clients may be mutating a chunk concurrently. So it's possible that you have a chunk and you have more than one application that's actually trying to change it at the same time. And so that means that not only do you have to make sure that the changes happen at all the replicas, but you have to make sure they happen in a consistent order. All right. So not just that they happen consistently, but they happen in the same order. Because obviously, if one chunk does ABC and another chunk does CDA, there's no guarantee that the final state of the chunk's data is going to be the same. Okay. And these are all standard distributed file system issues. It's not unique to GFS. So to handle this, the master grants what's called a chunk lease to one of the replicas. Which is designated the primary. Okay. And so the primary is responsible for choosing an order for all mutations to a chunk. So there's a whole bunch of advantages to this. One is that you might have wondered when we talked about mutating, or even reading was one thing. You don't care about a primary when you're reading because you're not changing anything. But writing, you might have wondered, like, do I have to write to all the replicas? No. You write to the primary. And the primary takes over from there and determines which replicas there are and what order the writes are going to occur in if multiple clients, multiple applications are trying to write to that chunk at the same time. So you only write to one primary chunk, and then automatically everything will be replicated correctly for you. Okay, you don't have to deal with any of that as an application. Okay, so all replicas are instructed to follow this order. For all mutations on a chunk. Okay. And Lisa's timeout after 60 seconds. But a primary can request a Lisa's extension. During a heartbeat communication. Okay, So what normally happens is that if a primary is sitting there doing nothing, after 60 seconds, someone else is going to get the leads, maybe the same primary, maybe one of the other replicas. And the primary doesn't care. He's like, whatever. All I know is that as the primary, the mutation request will come to me, and I'll be the one to decide what order to apply them in. But if nobody's talking to me, it doesn't matter whether you give the leads to someone else. However, if the primary is in the middle of an actional mutation, then you can't, or you don't want to, have somebody else become the primary all of a sudden, because that's going to be confusing. So what happens is if the primary is busy doing something, when the next heartbeat communication comes in, which is guaranteed to come in less than 60 seconds, the primary will just tell the master, oh, and by the way, I want that lease extended, which is basically his way of saying, I'm doing something and I need to continue to be the primary. When I'm done, if another 60 seconds goes by and I don't get asked to do anything, I'm not going to ask for another extension. You can give it to someone else. Okay? So that's how, at a very high level, the communication works, is that the master decides who the primary is for the replicas. And so when you ask to write to a file, you're going to actually get the metadata information from the master about who the primary is, and that's who you're going to communicate with. And then all you do is communicate with the primary as an application. You don't worry about how many replicas are there, are they getting updated, what order are they getting updated in, is everything working, is it consistent? The GFS system through the chunk server and the master are going to take care of all of that for you. Okay. And if something goes haywire, basically what will happen is when you try to do a write operation, you'll get an error back. And what that means is it didn't work. You don't know why, you don't care why, you just know that the write was not performed. And so as we'll see, what you'll do is you'll re-request the write usually, just to see is it going to work this time. And after a few re-requests, if you keep getting errors, you go back to the master and say, hey, this thing's not working. And the master will at that point have figured out, or will figure out, what's gone wrong, and it will probably give you a new primary to use for the writing. And it'll also guarantee that there's consistency. So it'll guarantee that the writes didn't work on some of the replicas, but not on the others. Okay. So everything will still be in the same state it was in when you tried that initial write and it failed. All right. So are there any questions about this sort of high level description? I'm going to give you an example tomorrow, Wednesday, of all the steps that get done when this happens, but that's basically how, as an application, you're being asked to write. And again, it's an attempt to minimize the amount of effort on the application. To make it as close as possible to writing to a local disk. Any questions about any of this? All seems pretty straightforward. All right, I'm going to let you go because we'll start talking about the details of mutation when we take up this topic again on Wednesday. Stay safe. Looks like the wind's died down here. So, and I'll see you in a couple of days. Thank you.
Thanks.
Thank you.